In this section, we'll be talking about the behavior of gases and how they behave when you change the temperature, the pressure, the amount of the gas, meaning like the number of particles in moles, and the volume of the gas. If at any time you need to pause to make sure that you can write down all the information, feel free to press pause and then you can continue the presentation. The behavior of gases is really due or best explained by what's called the kinetic molecular theory, or short for the KMT, kinetic molecular theory. The kinetic molecular theory is a theory which explains how gases behave based on the molecules that make up the gases and the amount of kinetic energy that they possess. So there are 4 basic principles within the kinetic molecular theory. Principle number 1 is the distance between the molecules is very far apart. This is what makes gases compressible. When you look at a picture of a solid and a liquid and a gas, you'll see that the solid is very close together. It's very organized. The liquid is also very close together, but not so organized. And the gas molecules completely spread out and take up the room of their container and the shape of their container. So because there is very much space between the gas molecules, you can compress a gas. And so you can think of an example of if you have a syringe and you put your finger over one end and you squeeze it, you're able to squeeze the syringe a little bit. You could not do that if you had a solid or a liquid in the syringe because those substances are already very dense. Principle number 2 says that the molecules have no intermolecular forces. So this is talking about an ideal gas. In the real world, you know that there are London dispersion forces and sometimes even different types of dipole-dipole forces that attract different particles within a gas. So we're talking about an ideal gas, in which case, the intermolecular forces have absolutely no attraction or repulsion for each other. So basically every particle of gas in whatever sample you're talking about is independent and acts independently from the other samples. Principle number 3 states that molecules are in constant random motion, colliding with each other and with the walls of their container. Keywords here are random motion and colliding. Random motion is important because what it says is that the molecules are moving constantly in any direction that they want to. If you think about kindergartners who've had a lot of sugar, maybe on Valentine's Day, they will run around a classroom in any direction. They run into each other, they run into desks, they run into the walls because they're just going crazy. Molecules within a gas are very similar because they have a lot of kinetic energy and they are going to collide with each other and collide with the walls of the container. So what's important about this principle is it tells us that the pressure that is exerted by a gas is due to it colliding with the walls of the container. So if you had, for example, a balloon, the balloon would be the walls of the container. So the molecules of gas within the balloon, as they collide with the wall of the balloon, that's what's making the balloon have its shape, and that's what's going to force the balloon to expand as you blow more air into it. If we continue with this analogy of the balloon, we can think about why the balloon takes a certain shape and why it expands equally. And that's because gas molecules spread out to take the volume of their container. Many of us learned sort of the phrase in 7th grade that liquids will have a defined volume but take the shape of their container. Solids have a defined shape and a defined volume. Gases take the shape of their container and take the volume of their container. And that's because the gas molecules are moving in constant random motion in every direction. So they're going to spread out to take up as much volume that their container will allow. Furthermore, these gases, as they move in constant random motion, they're going to exert pressure equally on all surfaces of the container because they are moving in every direction. So a balloon, when you are inflating a balloon, the molecules are going to be moving out from your mouth to the balloon, but from there they're going to move in all directions. That's why a balloon gets bigger in every direction. It doesn't just, get bigger off to the right or the left. It's going to expand equally in all directions. Finally, principle number 4 of the KMT, and this one is probably the most applicable to all molecules, meaning it will also apply to molecules in a solid or in a liquid, is that the kinetic energy of the molecules is proportional to the temperature of that substance. And in this case, we're talking about gases. You learned in the last unit that temperature, the definition of temperature in science terms, is the average kinetic energy of the molecules of the substance. So it would make sense that they are proportional. So what that means is that as you are increasing the kinetic energy of a substance, probably by adding heat or putting it over a Bunsen burner or on a hot plate. So as you add heat, you are passing kinetic energy into the molecules, and they are going to move faster. So the faster they move, the more kinetic energy they are showing. And as you take that average kinetic energy, we register that as the temperature. So as you're going to learn later in the next few slides, as you change the kinetic energy or the temperature of these molecules, you're also going to affect the pressure and the volume and the number of particles, and it's going to cause different changes to occur to the container of the gas. First relationship we're going to look at is the relationship between pressure and volume. And what this says is if you have a set amount of gas, meaning it is constant, you're not adding more, you're not letting some leak out. If it is at a constant temperature, so changing temperature is not a factor. If you change the pressure, that change is going to be inversely proportional to the change in volume. Inversely proportional means that as one goes up, the other one is going to go down. So it's sort of like a seesaw where as pressure goes up, volume goes down. For example, you could look at a container. And if you have a container that you compress, so as the volume gets smaller, that's going to cause pressure to increase. Let's look at a picture of this. In this picture, we see here a container which has a lid that can be moved. So if we take this container and we're assuming it is at a constant temperature because it doesn't show anywhere that we're getting hotter or colder, and we're assuming it is also a constant amount of gas, and if we wanted to, we could even count all of the individual gas particles here. But what we're going to do is we are going to decrease the volume of the container. So as the volume is decreased, the amount of space that is left for these molecules to move around in is much less. So they are much more likely to run into each other and to run into the walls of the container. So if there are more collisions with the wall of the container, such as you see with these molecules here, that means what you're going to have is an increase in pressure for this gas. This simulation available on Iowa State University's chemistry site shows how pressure varies inversely or is inversely proportional to volume. So what they have here is a pressure gauge, and this is connected to a syringe full of air. And if we, for example, take this plunger and we push it in, you can see that on the pressure gauge, the pressure is going up. So as I push it in further and further, pressure is going up because I am decreasing the volume of the room that those air molecules have. We can also do the opposite, where if we take the plunger and we pull it out to increase the volume for the air, we see that the pressure is going down. I can only pull the volume out a little bit, so you only see the pressure went down a little bit. And then as it goes back in, it goes back to normal. So I can do that again. If I pull the plunger out, the volume increases and pressure goes down. All of this is summed up in what's called Boyle's law. Boyle's law is just looking at pressure and volume independent of temperature and moles of gas. So Boyle's law is combined into the combined gas law. The second relationship we're going to look at is a change in temperature versus a change in volume. So in this case, we're keeping the other aspects or measurements of the gas constant. So we have a set amount of gas. We're going to have a constant pressure. And what we're going to do is we're going to look at how temperature change is directly proportional to change in volume. Inversely proportional, we said in the last slide, is as one goes up, the other goes down. Directly proportional means as one goes up, the other one is also going to go up, or if, as one goes down, the other goes down. So let's look at a picture of this. Here we have a sample of gas that is in a container, and that had the lid of this container is able to slide open. And we have it on, maybe this is a picture of a hot plate or a Bunsen burner, and the yellow color is indicating that it's warm, but maybe it's not hot. So we see that as this temperature goes from warm to hot, we see that what's happening is the top of this container is being pushed outward. So what's happening is but the molecules are trying to maintain a constant pressure. So there's a certain pressure here at the beginning. We could call this P1 or P initially, but let's say this pressure is 1 atmosphere. So as you heat the molecules, they're going to move faster, they're going to collide more often with each other in the walls of the container, and that would cause this pressure to increase. However, in order to relieve that pressure, to keep the pressure constant, these molecules are also going to be colliding with the top of the container, and they are going to slide that top up. As the top moves, this volume increases, which means the molecules are less likely to hit the walls of the container. So it will sort of decrease the pressure. So what that means is that this pressure, if we had a pressure gauge that we were able to monitor the pressure inside here, and then monitor the pressure at the end in here, it would be relatively similar. So as we see, as the temperature went up, the volume also went up. In this simulation from Iowa State University's Chem Department, they are showing us the effect of temperature on volume. This is Charles' law. Charles' law shows us that as you increase volume or temperature, they increase proportionally together. So as you increase the temperature, you will increase the volume. And we know that this could be because of a change in pressure. So a system is going to try and reach equilibrium. If you change the volume, you're going to affect the pressure of that gas, and it's going to want to go back to its same pressure that it was at. So it's going to either increase or decrease the volume to compensate for that change in pressure. So what we see is this is a syringe in some sort of a system. Maybe this is a syringe in a hot water bath, and there's a thermometer reading on it. And maybe this is a hot plate, and we can change the temperature of our hot plate in Kelvin. So as I change the temperature, I'm going to bring it up halfway. We can see that the volume on the syringe is slowly increasing. This simulation is also making a graph for us of volume versus temperature, so we can see that as temperature goes up, the volume is also going up. This is a directly proportional relationship. If this was inversely proportional, as Boyle's law is, the curve would be going in the opposite direction. Now, if we were to now cool this back off, we'll see that the graph goes back down, and we'll probably see that the plunger will go back down. So I will bring this back down to the coldest temperature they have for us here. And as expected, we see that the plunger's going back down. And what's happening is that the molecules are losing kinetic energy as they are getting cooled off, or at least as this system is losing energy. Energy's not being applied. So these molecules are losing kinetic energy. They move slower. They condense back together. And therefore, they're hitting the wall less, which is causing less pressure, which is allowing the volume to compress. And there we are back at our starting volume. We can also look at the relationship between temperature and pressure in a system where, again, it's a set amount of gas and it's at a constant volume. So this is a very similar situation we saw in the last slide, where what we saw is we had a container, but here we have these containers are capped. So we are not allowed to change the volume of this container. So what's going to happen as this sample of gas here, as it gets warmed up from warm to hot, we know that the molecules are going to move faster. They're going to collide more often with their container. And because they cannot increase the volume, the pressure is going to increase. So in the last slide, we saw that, in the last example, we saw that as the molecules moved the top of the lid up, they relieved their pressure. In this case, the volume is constant. This is a non-expandable container. So the volume is going to stay the same and the pressure will increase.